All right, so have you ever had that moment where you're looking at a graph, right? And it's supposed to be telling you about some kind of movement, maybe like a car speeding up or a ball bouncing, but it just feels, I don't know, kind of abstract.
Yeah, for sure.
Like you can see the lines and the curves and all that, but actually connecting that visual to the actual experience of motion, to what it's representing, well, it can be surprisingly tricky.
It really can.
It's easy to get kind of hung up on the details too, like, is this graph showing distinct steps or a continuous flow? What do these up and down directions even really represent in the real world? How can this little squiggle on a page actually capture something as dynamic as movement?
Well, what's interesting is graphs are incredibly efficient ways of conveying information, but they do rely on a level of abstract thinking. And that initial jump, right, from a concrete event to a symbolic representation, that can be a real hurdle for a lot of people.
Totally. And that's where this really cool idea of embodied learning environments comes in. So imagine if you were learning about these motion graphs, right? But you're actually moving yourself and you're seeing your movement instantly drawing a line on a screen. It's all about bringing your physical experience into the learning process. So it becomes a full body understanding.
Oh, that makes a lot of sense,
Yeah.
especially when you think about how we naturally learn in the first place. Like our earliest understanding of the world is through our senses, right, and through our actions in the world. Embodied learning really taps into that fundamental connection between our bodies and our brains.
It seems so obvious when you put it like that.
It does, doesn't it?
So for this deep dive, you have been going through mountains of research, looking at how this embodied learning idea has been used specifically for understanding motion graphs.
I have 44 different studies, to be precise, which cover 62 different learning environments that try to use the body in some way to teach about motion graphs.
Wow, that's a lot of data to sift through. So what's the mission for us today? What are we hoping to uncover?
Well, our mission today is to explore how these environments actually work. And really, the core question is what makes them effective, especially for someone like you, the listener, who wants to really grasp these complex ideas thoroughly but also efficiently.
A shortcut to deep knowledge. I like it.
Exactly. And with so many different approaches out there, it can be a bit overwhelming. So the review you shared actually offered a really helpful way to categorize all these different learning environments. It boils down to looking at two key aspects.
Right. The first one being bodily involvement.
Right.
So is the learning centered around your own physical movement? Or are you mostly observing the movement of someone or something else? Are you the one doing the moving or are you watching movement happen?
And the second key aspect is immediacy. So how directly and quickly is that motion, whether it's yours or something else's, connected to a graph?
Yeah.
Does the graph appear in real time as the movement happens? Or is it something that's created later after the movement has taken place?
Cool. So combining those two aspects, then that gives us four distinct ways that these embodied learning environments have been designed, right?
Exactly.
Okay. So let's dive into the first one, which is Class I.
Class I.
Immediate own motion. And this is where you are the one moving, and that movement is instantly generating a graph.
Yeah.
Now, the review highlighted that motion sensor technology. That gets used a lot in these kinds of activities. And it makes sense, right? Because it can capture your movement and display it immediately. But why is that immediate connection so powerful?
Well, think about it. Imagine you're walking towards a motion sensor, and as you're moving, it's detecting your changing distance from the sensor. And then, boom, a distance time graph just appears on a screen right in front of you. So you can see your every step, your pauses, everything, all translating into the shape of that line as it's being drawn.
Ah.
It's a very direct, visceral link between your body and the graph.
So like you're literally seeing your body creating that visual representation in real time.
You are. It's amazing.
So what are some examples of this in action?
Well, one study, for example, had students read a description of a movement first, and then they had to sketch a graph of what they thought that movement would create. And then they got to actually act it out in front of a motion sensor, and they got immediate feedback on a graphing calculator.
Yeah.
So they could compare their prediction, their sketch, to the actual graph their movement created.
That's fascinating.
It is, because it's that immediate comparison that allows for, well, real-time error correction and a deeper understanding of the relationship between what your body is doing and the line on the graph.
You're not just seeing the result, you're a part of the process of creating it.
Yeah, exactly.
Okay, and another example, this involves students trying to actually match like pre-drawn graphs,
Yeah.
distance time and velocity time graphs, by moving their hands in front of a sensor. So they could see their hand's motion getting graphed live on the screen. It's almost like their hand becomes a cursor or something, and they're physically tracing the shape of the graph.
And, it's not just limited to those kinds of movements.
Oh, really?
No. I mean, the review mentioned studies where students moved a motion sensor attached to a wheel, for example, and they could see the graph of the wheel's rotation generated in real time as they moved it,
So anything that's moving, you can track it and graph it.
basically. There was even one using a simple computer mouse. So you move the mouse on the pad, and that motion gets plotted simultaneously as a line on the screen. It's like even these small everyday movements can be used to build this understanding of how motion connects to a graph.
I mean, I'm thinking even just the act of physically creating the representation, right? Even if it's with a mouse, maybe that reinforces the concept in a different way.
Oh, absolutely. That direct manipulation, that immediate consequence, I think those are key elements in this type of learning.
Okay, so that's class 1, immediate own motion.
Right.
So let's move on to class 2,
Okay.
immediate others objects motion. So in this one, you might not be the one physically moving, at least, not in a way that's directly represented on the graph.
Right.
But you're either observing or you're influencing the motion of something else. And then, boom, the graph is generated immediately right along with that motion.
Makes sense.
Okay, so an example that really jumped out to me was controlling a pendulum.
Yeah.
You might give it a push, and as it swings back and forth, a motion sensor is tracking its movement. It's generating that graph live in real time. So you're interacting with the physical world, but the graph is showing the pendulum's behavior, not your hand giving it that initial push.
Exactly. It's your action that
Mhm.
sets things in motion, but then the focus shifts to what you're interacting with.
Interesting.
And then there's a whole bunch of really cool stuff happening with computer simulations that fall into this category too.
Okay.
Like one example is SimCalc Math Worlds. Have you heard of that?
I have.
So in that one, you can actually create or you can modify mathematical functions that dictate how an animated avatar moves on the screen.
Oh, cool.
So you see both the animation and the corresponding graph updating simultaneously.
Yeah.
It's almost like you're using the language of math to directly influence movement, and you see its graphical signature appear instantly.
So it's like you're the choreographer using equations, and then the graph that's like the dance notation that's appearing in real time. I love that analogy.
It's a good one.
Okay, now what about if I'm not controlling anything? Like, what if I'm just observing motion that's already happening?
Well, there are examples of that too. Like observing a simulation of an elevator, right, moving up and down, with its corresponding velocity time graph displayed alongside it.
So you're not controlling the elevator, you're just watching its motion unfold, and you see the immediate graphical translation of that.
Exactly.
Hmm.
And, it's not always just about digital simulations or these, like, inanimate objects.
Oh, okay.
The review mentioned teachers using their own bodies as the moving object.
Ah, that's interesting.
So the teacher's doing these hand movements, and those movements are being captured by a motion sensor. And then, boom, it's displayed as distance time and velocity time graphs in real time for the students to watch.
So the teacher becomes like the living embodiment of the graph.
They do,
Yeah.
which is super cool. I think, when you can see a familiar human movement like that, and then you see its immediate translation into a graph, it helps to bridge that gap between the abstract symbols on the page and something that you can relate to more directly through observation.
Okay, so that was class 2, right?
That's right.
Immediate others objects motion.
Right.
Now let's shift gears a bit to class 3, non-immediate own motion. So in this case, you are moving, but the graph isn't created in real time. There's a delay, right? The graphical representation, that comes later. So what's different here? Like, what kind of thinking is involved in this type of embodied learning?
Well, in this one, memory becomes a lot more important. And the ability to reconstruct the physical experience in your mind, right? So you have to recall how you moved and then connect those memories to the process of actually creating the graph later on. So that direct sensory link, that's broken here.
So you have to sort of hold that movement in your head and then translate it later.
You do.
Okay, that's interesting. What are some examples of class 3?
Well, one that really stood out to me was this activity where students walked at different speeds while carrying a leaky water bottle.
A leaky water bottle.
Yeah, it's kind of cool. The idea is that those drips of water, they leave a trail behind them on the floor. And by measuring the time intervals between drips and the distances between the drips, the students can then later construct position time graphs of their walk.
Well, that's clever. So the physical act leaves behind this, like, physical record.
Oh, data set, right?
Yeah, a data set that then gets analyzed.
Exactly. And there was even a study that intentionally put in a delay between the whole body motion and when the graphical representation was shown to the students.
Interesting.
And it was specifically to study how that time lag affected their ability to make those connections in their memory. Right.
Okay. So it highlights like how important that immediacy can be for learning sometimes.
It does,
Mm.
because when you remove that immediate feedback loop, then, well, the learning process has to rely more on your ability to remember information and then map that information onto the conventions of graph construction. It adds there's a whole other layer of cognitive challenge to the process.
That makes sense. Okay, and finally, we get to class 4, which is non-immediate others objects motion.
Right.
So in this one, you're observing the motion of other people, other objects, and the graph is created sometime after the motion has happened. This feels like a more, I don't know, a more traditional science experiment kind of setup.
It does, doesn't it? It's
Yeah.
that classic observation and analysis approach.
Totally. So in this category, you're more of an observer, a data analyst, right?
Yeah.
You watch something move, you collect information about its movement, and then you use that data to build the graph.
Right.
So what are some examples?
Well, there's the classic one, recording the time and distance of a rolling ball, right, using a spark timer. So that leaves behind little marks at regular time intervals, and then you use those marks to plot points and create a graph of the ball's motion.
So you're really hands-on with the data collection.
You are, very much so. And there's also, building ramps, rolling objects down them, and then manually measuring the distances traveled at different time points, and then using that data to draw graphs.
Yeah.
All of these classic physics experiments, they fall into this category. It's systematic data collection and interpretation to create a graphical representation.
Okay, so lots of hands-on measuring.
Right.
What else?
Well, observing a robot as it moves, and then using its distance and time data to construct distance time and velocity time graphs.
Yeah.
Or even like watching videotaped motion events and analyzing them frame by frame to, maybe count the distance an object moves between each frame, and then using that to create graphs later on.
So you're breaking it down into those tiny increments of movement.
You are.
Cool.
And the review even mentioned a study where students were shown graphs of an object's motion several minutes after they had watched a video of that same motion. So again, looking at the impact of that delay between seeing the motion and seeing its abstract representation in a graph.
Yeah.
And it's not all about, physical motion that you're directly observing.
Oh.
There are some really interesting examples that involved programming the movement of an animated object within software.
Oh, cool.
So you might write some code, like some algebraic code, or even sketch out a desired path on a graph, and then see the animation play out afterwards, with graphs plotted from the data of that resulting movement.
So you're almost working in reverse. You're not going from the motion to the graph. You're defining the motion through symbols or visuals, and then the graph is a consequence of that, right?
Exactly. The immediacy there, it's broken by that extra step of having to use a simulation to create the motion.
I see. Okay, so we've explored all these 4 different categories. So we've got immediate own motion, immediate others objects motion, and then the non-immediate own motion, and non-immediate others objects motion.
That's right. 4 distinct ways to use embodied learning to understand graphs.
So now the question is, why are some of these approaches seemingly more effective than others for helping people learn about motion graphs? In the review you shared, they identified 8 key factors that researchers think are really important in making these environments successful. Let's get into those.
Absolutely. I mean, these are like the special ingredients, the things that help learners really bridge that gap between the physical experience and that more abstract graphical representation.
So the first one is real-world context.
Okay.
And this is all about making the learning feel relevant, connected to things that students already understand, that they've experienced in their lives. Why is that connection so important, though?
Because when you can relate that motion that's being graphed, right, to something that's familiar to you, like the movement of a car or a person walking or an elevator, it gives you that mental anchor. It makes that abstract graph feel less alien and more like a representation of something that you can actually visualize and that you kind of intuitively understand.
It grounds it in your own experience in a way.
It does. Like, for example, studying a robot's motion, but doing it in a real-world setting, right, where you can see how that robot interacts with its environment, that's going to give you a much richer context than just looking at a simulation on a computer screen.
Oh, yeah, for sure.
Or even like recognizing the velocity profile of an elevator ride that you've actually taken.
Yeah.
That can make looking at a velocity time graph so much more meaningful.
Yeah, I get that. Okay, so the next one is multimodality.
Okay.
And this involves engaging multiple senses at the same time, right? So seeing the motion, feeling your body move, maybe even hearing sounds that are connected to that motion. Why is this kind of multisensory input so good for learning?
Well, our brains just process information better when they're getting it from a variety of different sources.
It's like they're getting confirmation from all these different channels, right?
Exactly. So when you're moving in front of a sensor and you're seeing that graph appear at the same time, you're getting this kinesthetic feedback,
Right.
right, from your sense of movement, and you're getting the visual feedback. And those two are reinforcing each other.
It's like double the learning.
It is, and it activates all these different neural pathways, which can lead to a much deeper, much stronger understanding.
That makes sense.
And, even something as simple as touching and tracing a graph on a computer screen,
Mm.
right, as you're thinking about that corresponding motion, that can enhance the learning process through, that tactile input as well.
Oh, interesting. Okay, so the next factor is linking motion to graph.
All right.
And this seems almost obvious, right? But it's all about explicitly and clearly connecting the movement, whether it's your own or something you're observing, to that graph.
Right.
But why is that explicit connection so vital? I mean, isn't it already there by definition?
Well, you would think so, but actually, without that clear, direct link, the graph can just stay this abstract symbol on a page, right? It can feel detached from the actual event that it represents. So the immediate feedback from a motion sensor, that's a great example of how to create that strong link.
Mm.
You move, and the graph changes right then and there. There's no question about the connection.
So there's no room for misinterpretation in a way.
And the review even suggests that that immediate coupling can improve memory, your ability to remember the relationship between the motion and the graph later on.
Oh, that's interesting.
Like, think about those examples we talked about where there was a delay between the movement and the feedback.
Mm.
The stronger that initial link, the better that memory is probably going to be.
Right, that makes sense. Okay, and another key factor is multiple representations.
Right,
So this is showing the same motion, but in different ways,
right.
not just one graph.
Not just one.
Maybe you have a position time graph, a velocity time graph, even an acceleration time graph for the same movement. Or maybe you're showing the graph along with a table of numbers, or that mathematical equation that describes the motion. Why is it helpful to see the same thing in so many different ways?
Well, each representation, each way of showing it, it highlights different aspects of that motion, right?
Mm-hmm.
And it also caters to different learning styles.
Yeah.
So some people might grasp it better by looking at that curve on a graph, while others might need that table of numbers, that concrete data, to really make sense of it.
Ah, I see.
And by seeing the same thing represented in all these different ways as that curve on a graph, a set of numbers in a table, that symbolic equation, well, you start to build this more complete, more holistic understanding of it. And even just acting out the motion physically, that can be considered another powerful form of representation. So now you're bringing in that kinesthetic understanding as well to complement the visual and the symbolic ones.
Yeah, it's like each way of seeing it adds another layer to your understanding.
Exactly.
Okay, so the next one is semiotics. And this one involves using symbols, signs, gestures, language,
Even metaphors, analogies.
all of that to build meaning around the graph, right?
Right.
So it's like creating that shared understanding, creating a vocabulary for interpreting these visual representations.
Exactly. Like using gestures, right, to emphasize how steep a line on a graph is
Hmm.
and connecting that to how fast the movement is in reality.
Ah, so you're like physically acting it out with your hands?
Right. Or even just using metaphors, simple things like the ball is climbing the slope of the graph
Yeah.
to describe, a position that's increasing. It makes those abstract concepts feel much more intuitive, much easier to grasp.
Cool.
Even the very idea, right, that a static line on a graph can actually represent fictive motion.
Oh, okay.
So that implied movement over time, even though nothing's actually moving on the page,
Right, right.
that relies on this kind of shared understanding, this shared interpretation.
Hmm. Okay, that's a good one. So what about student control? How does that play into effective learning?
Oh, well, student control, that's all about giving the learner that ability to actually manipulate either the motion itself or its graphical representation.
So they're not just passively observing.
No, they're active participants.
They're actually in the driver's seat. So why is that important?
Well, because when you have control, you can explore.
Right.
You can tinker. You can really start to understand those relationships between motion and graphs in a much deeper way.
I see.
So like directly manipulating a graph, maybe you're dragging points around, changing its shape, and then seeing how that affects a simulated motion. That allows for a lot of experimentation. It allows you to test out your hypotheses.
You get that instant feedback about what happens when you tweak things.
And similarly, if you're able to control the actual physical motion that's getting graphed, well, now you have this direct influence over the data itself, right, over the creation of that visual representation.
Ah, so it becomes a more active form of learning.
It does. And that active engagement, it can lead to much deeper understanding and much better retention of the knowledge.
Okay, cool. So then we've got attention capturing. What is that all about?
Well, attention capturing, that's referring to those aspects of the learning environment that are designed to draw your attention, your focus, to the most important details.
So it's like they're highlighting the key takeaways for you.
They are.
So how does that actually work? What are some ways to do that?
What could be visual cues,
Mm-hmm.
like maybe highlighting specific parts of the graph that correspond to certain moments in the motion.
Oh, I see.
So, for example, maybe you're watching a video of the motion.
Yeah.
And right next to it, you have the graph, and there are these visual links that connect specific points on the graph to moments in the video. So you can see very clearly how those two things relate to each other.
So there's no ambiguity about what's connected to what.
Right. Or, even something as simple as like changing the color of the line on the graph or making it thicker at those key points in the motion. That can really draw your eye to those moments.
Oh, that's a good one.
Or, like in the leaky water bottle example we talked about before, that pattern of drops itself captures attention and helps to represent the changing speed of the walker.
Right.
So it can take all sorts of forms.
Okay, and the final factor. This is cognitive conflict.
Right.
So cognitive conflict, that happens when you come across information that challenges what you already believe, right?
Mm.
What you already think is true. And it makes you kind of rethink things.
Exactly. It's that wait a minute moment that forces you to really examine your understanding.
So how can these embodied learning environments create that kind of productive conflict?
Well, think about this.
Mm-hmm.
Imagine you're moving in front of a motion sensor, and you're trying to create a flat line on a distance-time graph by standing perfectly still.
Okay.
But then when you look at the graph, it's not perfectly flat. It's got these little wobbles in it, right?
Well, that's because even when you think you're standing still, you're probably making these tiny, unintentional movements.
Right.
So now there's this conflict.
Right. Between what you expected to see and what's actually happening.
Exactly. And that forces you to refine your understanding of what standing still really means, especially in the context of precise measurement,
Yeah.
It makes you realize that even those tiny movements get captured by the sensor and represented on the graph.
Oh, that's a really good example. What else?
Well, or even just like disagreements between students during a group activity.
Ah.
Maybe they're trying to interpret a graph of a motion that they all experience together,
Yeah.
and there are different opinions about what the graph shows.
Well, they had to sort it out and come to a shared understanding.
Right. And those debates, those discussions that happen when there are those conflicting interpretations, those can lead to some really valuable learning moments.
I bet. Okay, so taking all of these different types of learning environments and all of these factors that can make them more or less effective.
What did the research seem to suggest about which approaches tend to produce the best results for understanding motion graphs?
Well, the review showed that those environments that really focused on the student's own motion and that linked it immediately to a visual representation, so that would be our class I from earlier.
Right. Oh, yeah.
Those consistently showed the most positive impacts on learning. And it makes sense when you think about it because those environments often incorporate several of the other factors that we just talked about, right?
Yeah.
Engaging multiple senses, providing that clear link between action and the graph, and using multiple representations of the same motion.
Yeah, it's like they're hitting all the high notes for effective learning.
Exactly.
And it seems pretty intuitive, too. You're actively involved. You get that instant feedback. You're experiencing the connection in this multisensory way. It's not just a bunch of abstract squiggles on a page anymore.
Right.
So what about observing the motion of other things?
Well, interestingly, the review suggested that learning just by watching other people move or by watching objects move without that direct, immediate connection to your own actions, so that would be our class 2 and class 4,
Right.
those approaches seem to be less consistently effective for really improving understanding of motion graphs.
So even though observation is still valuable, it seems like that active participation and that immediate feedback from your own movements, those are key for building that really strong intuitive grasp of what these graphs are showing.
That seems that way.
Now, were there any particular studies within that class I group that really stood out, like in terms of showing how powerful this approach can be?
There were. The review highlighted some really influential early studies that focused on this idea of students seeing the immediate graphical representation of their own movements. And those studies reported some pretty substantial positive effects on the students' understanding of distance time graphs, specifically. There was the work by Brassel back in 1987, and then there was research by Mockrose and Pinker also around the same time that were specifically mentioned in the review. And their findings really point to the potential of this type of embodied learning.
That's amazing. So, for you, the listener, the one who wants to truly deeply understand these dynamic concepts, the big takeaway here is that actively involving your own body, seeing your movements instantly translated into that visual graph, that can be a truly effective way to build a deep and lasting understanding of these often confusing motion graphs.
It can be. And it's worth noting how motion sensor technology keeps coming up as a key component of these most effective learning environments.
Yeah.
That ability to capture motion with that level of precision and immediacy, it seems like that's really crucial for making this kind of learning experience so powerful.
I'm really struck by this idea of how powerful it can be to connect our physical experiences to these abstract ideas?
I am too.
So I want to leave you with this thought. How could you apply these principles of embodied learning in your own life? And I don't just mean with motion graphs. How could you use direct experience, immediate feedback, and the linking of physical actions to abstract ideas? How could you use all of that to learn new skills? Or even to explain complex topics to other people, but in a way that's more intuitive, more grounded in their own experience? What other abstract concepts do you think could be made more tangible, more understandable through some kind of embodied learning experience?
I love that. It really gets you thinking about how much potential there is for this kind of learning.
It does. And the research we've been talking about today, well, it provides a pretty compelling case for how our brains might actually learn best when the learning is active, when it's grounded in those sensory experiences.
Right. It's about engaging our whole selves in the process, not just our minds.
Exactly. So hopefully this deep dive has given you a bit of a shortcut to understanding this really fascinating area of research and maybe even inspired you to think differently about how we learn and how we can make even the most abstract ideas a little bit more concrete. Thanks for joining us.
Thanks for having me.